So today we'd like to go a little farther with our study of gases. It all comes down to understanding this picture of a sample of gas moving around randomly inside of our container. We had a bunch of formulas so far. We had the kinetic energy of one particle. Which particle? The most probable speed particle. We had the kinetic energy of the average particle, which was much more useful. We had these two kinetic energies being able to be plugged in here to find the speed of the particle, either the average speed or the most probable speed. We had these two formulas that told us total energy inside the box. This is the one that's more important. Little n stands for moles, capital R is the ideal gas constant, T is the temperature in Kelvin. Okay, these are the terms you need to make sure you understand really clearly. Most of the study of gases comes down to these terms. So we have the idea of temperature. We spent the first week of this unit making sure you understood that temperature was a measure of kinetic energy. As the temperature goes up, the kinetic energy of these particles goes up. It is a direct relationship, if you're working in Kelvin, between temperature and kinetic energy. Pressure. We've talked about pressure in terms of fluids. We saw that pressure was measured in newtons per meter squared, or pascals. We learned how pressure with a fluid was caused by the weight of the fluid above you. With gases, pressure is caused by the particles hitting the walls of the container. Every time these particles hit the wall, they create a little bit of pressure. A force is required to stop the particle and make the particle move in the other direction. The amount of pressure is determined by a few things, and hopefully they're obvious. How fast the particles are moving. The faster they move, the harder they hit the walls. The mass of the particles. When they're more massive, they're going to deliver a bigger punch to the walls. How often they hit the walls. If the particle hits and then doesn't hit that wall again for a long time, the pressure on average is going to be kind of low. And finally, the number of particles in the box, because every particle that hits the wall is another example of pressure. So we have lots of different things that determine the pressure, but the pressure is caused again when these particles hit the wall, the floor, or the ceiling of the container, or also if they hit each other. Okay, if this is my container and these are gas molecules, every time these particles hit the wall, they create a little bit of pressure. Again, the pressure should be measured in pascals, which stands for newtons per meter squared. Volume is how big the container is, and as always, we measure our volume in meters cubed. A meter by a meter by a meter. Okay, so a meter cubed is quite a big amount of volume. Finally, number of particles, and again, for convenience, we measure that in moles. We saw how if you take your number of moles and multiply by Avogadro's number, you get the actual number of particles, but usually it's more convenient to measure in moles. Okay, so from this we get a couple of equations that are really important that I think you've seen before in your chemistry class. Okay, and they are the ideal gas law and the combined gas law. It turns out that the pressure times the volume is equal to the number of moles times the temperature times the ideal gas constant, which is again 8.31. The pressure has to be in pascals, the volume has to be in meters cubed, the temperature has to be in Kelvin for this to work out. And when you use those units, you'll get 8.31 as your ideal molar gas constant. Okay, sometimes you might want to bring the temperature to the other side. These are the three main variables, the pressure, the volume, and the temperature. And they're equal to N times R. Just a different way of writing it. However, this is important. If your container is sealed so that no particles can get in or out, that means that this N is also constant. So this entire side of the equation is a constant. And what that means is that the pressure times the volume divided by the temperature is constant. So if you get the pressure, volume, and temperature at one moment in time, it will equal the pressure times the volume over the temperature at another moment in time. This is a more advantageous way of solving some problems in comparison to the ideal gas law. It comes from the ideal gas law. It's not really a new law. It's not really a new equation. It's just a different way of dealing with an ideal gas when, this is important, when the container is sealed and no particles can get in or out. Okay, when you're using this, there's another advantage, and that is as long as you use the same unit for pressure or volume, it's legal. You don't have to work in pascals. You don't have to work in cubic meters. So you can work whatever unit is convenient for pressure and volume. However, this is important. Temperature still has to be in Kelvin. Celsius and Fahrenheit are not actual measurements of temperature. 0 Celsius does not mean the particles stop moving. 0 Fahrenheit does not mean the particles stop moving. They are not valid units to use for temperature in this equation. Pressure and volume, anything goes. Okay, so we're going to have two main equations. We've already learned them. And they are PV equals nRT. That relates the pressure, the volume, and the temperature, and the number of particles all together for your gas. And then the one we had earlier, which is the energy of the particles inside the box. These are going to be the foundational equations when we start looking at things like engines and air conditioners and heat pumps and refrigerators. Okay, we want to know how much energy we can get out of these things. These are the formulas. Energy of the particles inside the box, and then the relationship between the pressure, the volume, and the temperature. We will practice these equations tomorrow.